Hello everyone, I'm Xuemei from CWI and to dive to the Netherlands. Today I will introduce our work about visual saliency. And before we get into the real work, I would like everyone to know the importance of visual saliency because it can help with point cloud compression algorithm or transmission pipeline or quality assessment. And the other problem is there are many different algorithms for detect or predict the visual saliency. But there are many other metrics that already existing for compare the similarity of visual saliency map onto the content, for example, image. But there is no such a metric existing for point cloud. And to give more context, we have already done an experiment before to collect the visual saliency data of some dynamic point cloud sequences. In our previous work, we collected the QAVA-DPC dataset, and now we are creating another dataset under another situation. And here is the overview of the content that we used. There are some overlap with our previous work. And since our only variable is the with task or without task, so we keep other hardware, software exactly the same. And you can see here from the video how we actually get all the visual saliency data. So people need to go through 3 steps. The first one is the calibration, which we used the file.calibration provided by HTC Vive Pro I itself. And after the calibration successfully, people can step into the next thing, which is our real experiment to watch the video of point cloud. And the video will loop 3 times to give the user enough time to collect the gaze data. And at the same time, we also recording the trajectory of the people. And after people done with this, in our previous study, this is quite important. People need to think, oh, what's the quality of this point cloud? And from fair or good. But in our current study, people are informed you can watch the point cloud as free as you want, and there is no other task. Your only task is watch the point cloud, and then you go to the next error profiling thing to give you more accurate data. And after this, you can switch to the next point cloud. So the only difference is with the perceptual quality assessment task or without. After we get this, we follow exactly the same data processing pipeline to get the final visual science map. And the experiment results is from 4 perspectives. The first one is human-centered analysis of the movement of the user on the physical space. The second one is just to analyze the gaze data to get the final visual science map. And then we also analyze the SSQ and IPQ data from our questionnaire. Finally, we use semantic analysis from our interview to get this quantitative results. So in total, we have both the quantitative results and the qualitative results. Here I only show you the movement of the user, like the trajectory on the physical space. The red dot represents the movement of the point cloud, and the heat map is the trajectory of the user. You can say like with high motion point cloud, people tend to move a lot. The area is larger than this one, and the people tend to find a specific spot to get the information they want. But if you are not moving, then the user just walk around randomly. And for the other analysis, you can refer to our paper for more detail. And the final goal is the comparison between task-dependent and task-free. And first, we want to compare the consistency of the statistics of the gaze. And then we compare the final result, our visual science map, under 2 different scenarios. And we have a short summary about that. So the first thing, we analyze like the fixation, the volume of interest, like people focus on this silent area, like what's their volume, and then it's like the spread of the distribution of all the silent area. And the conclusion is like people tend to have more fixation, more VOI, and more spread of distribution under task-dependent scenario compared with task-free. And that is quite understandable because in task-dependent scenario, we ask you to evaluate the quality of the point cloud, which means the user need more cues or information to distinguish between between the difference of the quality. So they will more focus, so they will have more fixation, etc. The only exception is for the high motion content, because the high motion content is already like hidden enough information for the user to explore. So they basically has the same volume of interest and even more spread of the distribution of the gaze. And then we analyze the final result, the visual science map, and we proposed or adapted one algorithm called Earth mover distance to compare the 2 different visual science map. And the other one is widely used Pearson correlation. And for 300 frames, we can see that they're quite different. Otherwise, there will be overlapping enough. And we also plot all the visual science map for the other 4 content. We can also say they're quite different. And we also show you like the similarity average over 3 frames for each content. We can see that the score is quite low, which means they're different. A short summary, like why the proposed like EMD metric is better than the generally like Pearson correlation. For example, when EMD says like frame 58 is the most similar one, and for the same sequence soldier, and PCC identify 61 frame is the most similar one, And from the front view, we can see that they are really quite similar, right? And also here, at least they have something are the same. But if PCC say they are similar, I mean, from the leg and the back view, they are not similar at all. So that's why I think EMD is better than PCC. And for the details, there are like mainly adaptations, like how we adapt the EMD to from 2D to 3D. You can refer to our paper for more details. And finally, we got this beautiful plot. The red color is from task dependent, and the the blue color, and the red color is from like task free. You can see they are really quite different over time. That's all. Thank you.